You can see the screen. Very good. So again, I remind you, let me write on the screen a little bit. I will remind you about the situation regarding orbifolds. And the situation regarding orbifolds is this. So here I imagine just one chart. Here. And this is M, and then I divide by G, and I get X. But notice the font I'm using. This is not just X could be just the space, but X. Well, I want to remember all this kind of story when I write this X. So I don't know what I did. I pressed the wrong button. Do it. So we were going to interpret this as a category. So typically, if this is M and G is acting, and there is a point X here, M, and there is this arrow. The arrow, I will call it M, G, and then this will be MG. And this will be a category whose objects are M. M is the objects. It's a set, it's a small category, and the M is the set of objects, but it's a smooth manifold. And because the group is acting smoothly, namely G acts, every G in G acts by a diffeomorphism, well, here is what this category looks like for just G acting on M. So that's the category. This category is a groupoid because every arrow has an inverse. This is the inverse of this arrow, and every arrow has an inverse, so it's not only category, it is a groupoid. And again, the classifying space is denoted by Bx to a groupoid. And the basic idea is that we're going to have, whenever we have an arrow, we're going to put an actual segment there. And whenever we have a commutative triangle of arrows, we're going to put a 2 cell there, and so on, and so on, and so forth. We put cells, we form the classifying space, we draw an edge, and then we add a 2 cell, a 2 simplex for every commutative triangle in the graph. And we do this can be done for any category. Well, any small category admits the same procedure. the notation is has to do with Borel. The B is in honor of Borel, but I think the notation is Steenrod's. And the basic idea is that we used to have a BG in the past. We used to have a BG for a GA group. This is interesting even for a finite group. This is interesting even for C2. The classical BC2, what is the category that has two arrows? The identity arrow and then the other arrow, so that the arrow with the arrow is the identity arrow. Even this small category called Z2, BZ2 is interesting. It is an interesting, maybe not entirely trivial exercise to show that it is homotopy.
Yeah, RP infinity, right?
Homotopy equivalent to RP infinity. Yeah. So even the simplest groups give these interesting spaces. Even the simplest categories give these interesting spaces. Seagal 1968 does it for any category, not only for groups, and it is very useful to have it for every category. This is not, though, this is not homomorphic to Milnor's construction of BG. There is this famous Milnor joint construction. Milnor joint construction. It's very beautiful, but it's not, in some ways, the correct functorial construction. Seagal's construction of BG, Graham points out that was inspired by Grothendieck, conversations of one way or another. And then you have Seagal's BG, and then you have Milnor's BG. They are homotopy equivalent, of course, but this is a much more functorial construction. The one that I just described is much more functorial. It's easier to prove, of course, because BG is only a homotopy type and BC is only a homotopy type. You should not think of BC really as a space properly, but only the homotopy type of the space.
So just one question: if you have two equivalent categories, like does it produce homotopy equivalent?
Yeah, and this is very easy to prove in Seagal's, and this is proved in Seagal 1968, but it would be very hard for Milnor's joints construction. So that's one of that statement is an example of why Seagal's construction is so much nicer for certain things. It's good to know both constructions. But indeed, if you have Z equivalent category to B, I don't know, then BC is homotopy equivalent to BB.
But Milnor's construction, is it smaller in some sense, or does it produce somewhat more?
It has like less points, like it's
exactly
crushed. Yeah, and that's why it's harder to move around. Anyway, if I have this groupoid, think only of this example, for example, but then you would have a more general orbifolds. And an explanation of, detailed explanation of this is in my paper with Bernardo Uribe called Ghost Loop Spaces. But anyway, there you have Bx, then you have the topological space, just the quotient space. Just the quotient space, the topological space. This is just M mod G. And above every point here, the fibers change very much from point to point. because the fiber is the stabilizer, the classifying space of the stabilizer at every point. You see what I mean? Misha?
Yeah, you disappeared for a second.
Well, you see more or less this diagram that I'm explaining here.
Yes.
Yeah, that diagram is here, but what you asked us, it wasn't clear.
Well, again, if I have the orbifold, and I take its classified space of these groupoids, then I have a map that goes to just the quotient space. And the fiber at every point, the fibers change from point to point very much so, because the fiber of every point is a classified space of the group stabilizing X.
This is quite clear, actually. So this is more or less, well, I don't know if it's obvious, but I don't think it's hard to prove.
No, it's not hard to prove. But it is useful, because if now you work in rational homotopy theory, so you compute rational homology, rational, you see, the rational homology of a finite group is nothing. More, the rational homotopy type of BGX rationally is a point. So rationally, in the world of rational homotopy theory, Bx is X. So if you are just looking at rational homotopy theory, Bx is just X. And this is a useful remark. And if you are in the search of homology for orbifolds, this may be a little bit of bad news. You see what I mean?
Yes.
Because if you just compute the rational homology of Bx, you are going to get just the rational homology of X, and that's very boring. I mean, this forgot all the orbifold structure, just the quotient space. For example, if you just compute the rational homology, I mean, group cohomology is interesting, but rationally is not interesting. And group cohomology is not only interesting, it's extremely interesting. The best book around is the book of Alejandro Adem and Jim Milgram. It's an incredible book. And there you will compute these for many, many, many groups. But it is entirely different business than the very trivial task of computing this. Just a note of warning, group cohomology is extremely interesting, but not over the rationals. It's just as hard as it gets. It's one of the most important and harder problems in mathematics, compute group cohomology. Group cohomology, maybe I should say this, group cohomology or homology is by definition this. But of course, an algebraist will not tell you this definition. It will tell you, oh, you form a complex with the group structure G. And then you form this complex, and then you la 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 la, and then you form this differential, and that's the definition of group cohomology. This definition, though, has an advantage over the other definitions, even a computational advantage, and is that by not marrying your definition to one particular complex, but any other complex that could compute the homology of this homotopy type, gives you flexibility. In the case of M mod G, this is now, it's called the Borel B, remember, Borel B construction of the group action. And is the famous M cross EG divided by G. And in that part, that's equivalent, homotopy equivalent. Depending on your definitions, is equal or homotopy equivalent. And there is this beautiful book of Ike Murdoch where he says what BX classifies in the general case of local orbifold charts. It does classify something, but let me not go into that. So now, thing is, and this is exactly related to the remark that Misha was making before. Misha was telling us that if categories are equivalent, they're classified in space are homotopy equivalent, which is true, as in Seagal's paper. Very beautiful paper, classic. But here, there is a particular case of this remark. That is, if I change the orbifold atlas, I change the groupoid. To have different groupoids for the same orbifolds is to have different atlases for the same orbifold. And you would say, well, if I do the construction for a different atlas, if I have a complicated orbifold with local charts, and then I change the atlas, and I do the classified space of the different categories, I'm going to get a different thing. But the answer is no. You are going to get the same homotopy type. And this is a particular, changing the atlas is a particular case of equivalence of categories mentioned before by Misha. So the homotopy type of this orbifold, so to speak, is well defined. You see what I mean?
Yes, yes.
And this will be a homotopy type associated to an orbifold. And Leida has a paper where he does this a little bit better, and I recommend it. But you can think at first level of approximation just in this way. So in the search of cohomology, well, we would like a cohomology theory that gives you the appropriate Euler characteristic. And one would like perhaps equivariant cohomology. So what is equivariant cohomology? It's a generalization of group cohomology. Equivariant cohomology of a point is group cohomology. And this is interesting and it's important, it's very used in mathematics. But it does not quite, does not quite recover this notion of the Thurston, Conway and Thurston on the Euler characteristic, the orbifold Euler characteristic. You would like the Euler characteristic of this cohomology to be the orbifold Euler characteristic, and this is just not the case. Consider the orbifold a point, G acting on a point, consisting of a finite group acting on a single point. Then the Euler characteristic of these orbifolds becomes the number of pairs of commuting elements in G divided by the order of G. And this, as an exercise, is the same as the number of conjugacy classes of elements in G. And so that's the orbifold Euler characteristic of these orbifolds, which will not be recovered with the very sophisticated device that is group cohomology. So there is a discrepancy here for orbifolds. Of course, for many folds, they do coincide. Because this, for many folds, this becomes just the cohomology of M, and we know, yes, that the orbifold characteristic is the Euler characteristic of M, and we know the Euler characteristic of M is indeed related to the classical cohomology of M. It's just the alternated sum of the Betti numbers. But not so for orbifolds. The relation breaks down. You see what I mean?
Yes. Yes.
So what does one do? Given a finite group, there is the group cohomology, super hard, and there is the representation ring, isn't it? And the representation ring is called the K-theory of the equivariant K-theory of a point acting on by G. That's the representation ring. It's a ring. It's no longer just a vector space. It's bona fide ring. So one would like to one would say, well, maybe why not? What if I use equivariant K theory? And there is a also in the again going back to Graham-Segal, if it was just global quotients with one chart like this, like here, but you had two ways of representing the same orbifold, two very different charts. Let me give you an example. Suppose that you have a disk and then you divide it by Z mod 4. And then you get this thing. You see what I mean?
Yes.
But now you have two disks and you divide it by Z mod 4 cross Z mod 2. Z mod 2 just exchanges the disks. You see what I mean?
Yes. Okay. What will
Then
happen?
I get the same orbifolds.
Yes.
The group is very different. The manifold is very different, but it's the same orbifolds. Of course, I could do it much worse than that, much more complicated situations. So I could have very different groups, very different manifolds, and get the same orbifolds. But there is this, from the paper of Graham, called equivariant K-theory, this is true. And it is true, and this is a theorem of, I don't know, I think this is Doré-Tronc and Mordyke, that for general orbifolds it's still true that the equivariant K-theory is the same. This is also Adem and Ruan, and Uribe and myself in various contexts. In any case, orbifold K-theory is well defined. Independent of the representation. Remember that equivariant K-theory was just the theory of equivariant vector bond, if M is compact. Otherwise, well, you have to think harder. You get equivariant vector bundles over M and things like that. Form this Grothendieck group of equivariant vector bundles. If you have an equivariant vector bundle over a point, it's a representation. It's the same thing as a representation. And the Grothendieck group of representations is the representation ring of G. Okay?
Yes.
So, Atiyah and Segal observed that using the Segal character of an equivariant vector bundle, there is the character of a representation. Well, Graham-Segal defined the character of an equivariant vector bundle. Well, so what is that? So you have this equivariant K-theory is bundles over M, a G action on M, and this action extends linearly to the bundle. Fiber was linearly, and if you have a fixed point, notice, then the inverse image, the fiber at that point of the action, becomes a representation of G. And in general, it becomes a representation of the stabilizer of G. So you have all these representations in an equivariant vector bundle. And the Sigal character generalizes the notion of the character of a representation, and is a map that goes from the equivariant vector, the equivariant. Now, notice that while rational cohomology saw nothing, rational K-theory, even over the complex numbers, sees a lot. So there is this, traditionally the character was a class function, namely a function over conjugacy classes, if you remember this kind of thing.
Mm-hmm.
And now we have the character of an equivariant vector bundle is a bunch of vector bundles over the fixed point sets. Mg is the fixed point set of G.
Mm-hmm.
And there is the invariance or co-invariance for a finite group, it doesn't matter. This is the CG invariance. And there is this map, and the map is given by this. This is the formula of Gram-Segal. You restrict the vector bond, the equivariant vector bond to fixed points, and then you take the eigenspace of this G.
What is? Oh yeah, I see. The roots of unity. Okay. Okay, very good.
And this is an isomorphism. It's a theorem of Gram-Segal that this is an isomorphism. And this is called Segal localization. A beautiful theorem. And notice that it localizes equivariant K-theory. These objects here are equivariant vector, and these are ordinary vector bundles, no longer equivariant. These are ordinary vector bundles, no longer equivariant vector bundles. So when M is a point, this recovers the usual theory of characters for the finite dimensional representations of a finite group. And if you think about it, it's a nice exercise. The Euler characteristic of equivariant K-theory turns out to be Orbifold Euler characteristic. So Segal recovers all these elaborate discussions of a rather intuitive character of Conway and Thurston into something that you can use in theory, in structure theory of algebraic topology. You see what
Yes. Oh, it's beautiful indeed.
So, so this is the Orbifold characteristic has most to do with representation theory, so to speak, than with. Of course, you said, but why ordinary cohomology detected the Euler characteristic without groups in classical mathematics? And I going to say by mistake. because ordinary cohomology is isomorphic to K-theory for when there is no groups.
Okay.
But this is a mistake. This is an error. This is a so Euler. We were lucky historically to detect Euler characteristic by simplices by error. I claim.
But still, this Euler characteristic of Orbifold cohomology, it should be something meaningful, right?
Well, Conway and Thurston do it by simplices and count half simplices and this.
Yeah. Okay.
So I'm being saying that it's that the original thing was an error. You see what I mean?
Yes. Yes.
But I'm trying to stress the point that we're going towards the derived category, towards this kind of thing as a notion of space, and that simplices and triangles and these things were an historical error. It's a crazy thing to say, but it has a kind of a point from certain twisted point of view. You see what I mean?
Yes.
Do notice though that I'm taking that the Euler characteristic, I'm getting it as the Euler characteristics of things, of classical things, the ordinary Euler characteristic of classical things, but other things. Localization is trivial in the classical case. Here I need localization. You see?
Yes.
In any case, this is a definition of Chen-Ruan cohomology.
Okay. But do you really have to tensor with C?
Well, no. No, I can just define it without this. It's a definition.
Yeah, but you might lose some interesting things, right?
No. I mean, you may win some interesting things by having this weird thing.
Okay.
So it's the definition. And this is the way I got to the definition of stringy Chen-Ruan cohomology. There's many ways to get at it. This is my way to get at it.
Okay.
This is a classical mathematical way to get at it. Then there is the stringy version to get at it. For the stringy version to get at it, I recommend the paper of Uribe and myself called Gauss loop space. There the relation to this is also Hochschild. This for a more slightly more sophisticated point of view is Hochschild, and this is K theory, and there is a relation between Hochschild and K theory. When you think of Hochschild of a non-commutative thing.
So it's Chern character, right? This relation somehow, or not exactly? Yeah. Okay.
Yeah. The Hochschild of a non-commutative thing. This is the Hochschild.
Yeah, very nice.
In any case, it is the correct Euler characteristic. It's comparable with non-commutative geometry, and it has the correct partition function for quantum field theory, as we will see. So, we went today in search of Orbifold cohomology, and we found it. Notice though that if G is trivial, H stringy of M is H of M. But if G is if M is trivial, then H stringy of point mod G is Hochschild of G.
Okay. Okay.
And that's all for today. Thank you very much.
Yeah, very nice. Thanks a lot. So, do I have questions? Well, I will ask you later, but very interesting. Thank you.